All right, we're going to begin chapter 5, section 2, where we talk about trig functions. All right, so there's a lot of information on this slide, but let's just relate it with information that you guys already know, right? Some of this stuff, no. A lot of this stuff is new in terms of how we word the questions, but we can relate it to things that you guys have learned before, like in geometry. All right, so for instance, we see on the screen a sine, a cosine, and a tangent, right? And you guys know sine, cosine, and tangent with SOHCAHTOA, right? Sine is opposite over hypotenuse. So let me write that down. Hopefully you remember this, right? Sine is opposite over hypotenuse, right? Cosine was adjacent over hypotenuse, and tangent of an angle is opposite over adjacent. And these specifically relate to a right triangle, right? So for instance, if I have a right triangle, that's my right angle, and this is my angle theta, right? This is my opposite side, this is my adjacent side, and then this is my hypotenuse, all right? Now, what we're going to do is similar to the last lesson, is we're going to relate this to a coordinate plane, right? We're going to relate these to angles in a coordinate plane. I'm going to show you what this would look like. Let's just say if we have a point in the first quadrant, right? So let's just say I have a point x comma y in the first quadrant. I'm going to plot it right there, right? Just using this image that we already have. And I'm going to say I have an angle in standard position, right? If you remember from the last lesson, standard position just has a vertex at the origin, an initial side on the x-axis, and a terminal side somewhere, right? It can be anywhere. And then that's going to form this angle theta right here, all right? Now, if I were to take this point right here, this point P, and drop it so that it touches the x-axis, we're going to get a right triangle, right? So we see a right angle in here, and if we have a right triangle, then I can find the trig function, the trig values at this angle theta, right? And so with respect to this angle, I have the opposite side is this one, and that's going to relate to the y coordinate of that point, all right? So the y, again, is the vertical distance from that point to the x-axis. And then similarly, I have the x value right next to it. This is the adjacent, all right? That's the distance from that point to the y-axis, right? And so I have an x and a y representing an adjacent and an opposite. And then I have across this right angle the hypotenuse, which we call r, right? R actually stands for radius. I know we don't see any circles here, but you're going to see in a couple lessons from now that circles and triangles actually have a lot more to do with each other than you might assume, right? So, but that's how this relates to the sine, cosine, and tangent that you guys are familiar with, right? And I can do the exact same thing in the second quadrant, right? I can take a point in the second quadrant and drop it so that the point touches the x-axis. And then if this is my angle theta, I have another little angle inside of here where I can create a right triangle as well, right? I have an opposite side, which is my y. I have an adjacent side, which is the x, and then I have an opposite, not an opposite, hypotenuse, which is that r value that I talked about before, right? So you can still do SOHCAHTOA using those values, right? And again, I just got this from a point in the coordinate plane and drawing the angle from it. And then again, you can do the exact same thing here in the third quadrant. So I can take a point in the third quadrant, connect it to the x-axis, and then we get the same thing, right? The opposite is going to be the y, the adjacent's the x, the hypotenuse is the r. All right, same exact thing in the fourth quadrant, right? I take a point, connect it to the x-axis, I get a right angle, and then my opposite is y, adjacent is x, and hypotenuse is r. All right, so in this lesson, you're not going to see me use SOHCAHTOA a lot. I'm really just going to use the x, y, and r notation for sine, cosine, and tangent. All right, so in all of these images down here, right, the opposite side was the y value, right? So y, y, and then y and y, right? Y and y. The opposite is always the y. So sine of theta is going to be the opposite, and then the hypotenuse we said is r. So opposite over hypotenuse. That means in a coordinate plane, sine of theta is always y over r. Similarly, cosine of theta is adjacent over hypotenuse, and in all of those images, adjacent was the x and the hypotenuse is r, and then tangent is opposite over adjacent. So the opposite, again, is the y, the adjacent is the x, all right? And then to get your other trig values, all you have to do is flip them, right? So these are new to you guys probably, right? So this CSC stands for cosecant. And all it is it's just the reciprocal of sine, right? So sine and cosecant go together. Secant and cosine go together, right? So SEC is secant. And then cosine is going to get you secant if you flip it. So notice that this one's r over x. And then COT stands for cotangent. All right, and then cotangent and tangent go together. All right, cotangent and tangent are pretty easy to remember. To remember cosecant and secant, I think if you need to flip it, well, then you should also probably flip the letters as well, right? S should go with the C, and this C should go with the S, all right? So cosine wouldn't go with cosecant, right? It would have to flip and go with secant, right? So one way to remember it, right? But these are the 6 trig functions that we're going to discuss in this particular lesson. What we also have above in words is we have r is the distance from the origin to that point, and we can get that using Pythagorean theorem, right? So if you guys remember Pythagorean theorem, it was a squared plus b squared equals c squared. In this particular instance, we're going to call it x squared plus y squared equals r squared, all right? Where x is a leg, y is also a leg, and r is the hypotenuse, all right? So let's put all of this in a problem. I'll show you what a problem might look like in these kinds of, in this lesson, all right? So I have a terminal side of an angle in standard position passes through the point 815, and we're asked to find the 6 trig values of theta, all right? When you're first doing this, I would definitely start by just sketching a little picture of what this might look like, all right? So I know the point 815, I'm going to say 8 is somewhere right there, and 15 is somewhere right there, right? So I have a point right there. And it says that the terminal side of an angle passes through this point. Again, an angle in standard position, I'm just going to draw a little ray, and then I have that this is our angle theta, all right? Now, if I take that angle and if I take that point and I were to drop it so that it touches the x-axis, notice that we have a right triangle now, all right? We have a right triangle along that side, all right? And then again, if you think about SOHCAHTOA, the opposite of this angle is going to be your y value, right? And your y value in this case is 15. Your adjacent in this case is this horizontal distance, and we get that it's the x value, right? So x equals 8. And now the only thing that we don't have is this r value, our hypotenuse, all right? To get it, we're going to use the formula x squared plus y squared equals r squared. All right, so I'm going to do 8 squared plus 15 squared equals r squared. So this is going to get us 64 plus 225 equals r squared. And so this is going to get us 289 equals r squared. And then you square root and you get r is 17. All right. Now, why didn't I put plus minus? Because r is a distance. It's the distance from the origin to that point. It's never going to be a negative number, right? So r in this case is 17, all right? So now I have everything I need to answer this question. I have that x equals 8, y equals 15, and r equals 17. So now I'm going to find the 6 trig values, right? When it says 6 trig values, it's sine, cosine, tangent, and their reciprocals, right? So sine, cosine, tangent, and and I want to find the reciprocals. So cosecant, secant, and cotangent. All right. Now remember, sine is y over r, and y in this case is 15, r is 17, so that's our answer for this one. Cosine is x over r, all right, which is going to get you 8 over 17, and that's your answer. Tangent is y over x, so this is going to make this 15 over 8, all right? Cosecant, secant, and cotangent, you're just going to flip them, right? So cosecant is going to be r over y, so 17 over 15. Secant is going to be r over x, which is 17 over 8. And cotangent is going to be x over y, which is 8 over 15. And then just like that, we get our 6 trig values. That's all we had to do. We answered the question. All right. Let's try the exact same thing with the next one. All right. So it's the exact same kind of question. We have the terminal side of an angle passes through -3, -4. I would just sketch it, right? The more you do these, you're probably not going to have to sketch it. That's totally fine. If you already know that that's x, that's y, and then you do the x squared plus y squared equals r squared. I just like to show you guys where that idea comes from. So -3 and then -4 is going to get you a point somewhere right there. So I have that the terminal side passes through that point right there. So then it's going to go something like that. And then if I connect that point to the x-axis, we get a little right triangle. And then we can do our opposite, which is our y, our adjacent, which is our x, and then our hypotenuse, which is r. All right? Now, again, you don't really have to draw that information out if you already know how to set up these kinds of problems, right? So I know that this is going to be an x squared plus y squared equals r squared situation, right? So I'm going to have a -3 squared plus -4 squared equals r squared. And then we get 9 plus 16 equals r squared. So 25 equals r squared, square root both sides, and I get r is 5. Again, no plus minus just because r is the distance, right? X and y can be negative, but r has to be positive always, all right? And now I have that x equals -3, y equals -4, and r equals 5. All right? So now I can find the 6 trig values. I know that sine has to be y over r, which is -4 over 5. All right? I know cosine is x over r, which is -3 over 5. All right? And I know tangent has to be y over x, which is -4 over -3, which is 4/3 positive, all right? And then to find the others, right, sine and cosecant go together. So to find cosecant, I'm just going to flip what we got for sine, right? So it's going to be -5 over 4 then, all right? Cosine goes to secant. So I know secant has to be the flipped. It's going to be -5 over 3, all right? And then I know cotangent has to be the flipped of tangent. So it's going to be -3 over -4, which is just +3 over 4. All right, and then those are my 6 trig functions of this problem. All right, so that's in general how we do these kinds of problems when they give you a point and you need to find the 6 trig values. All right, so now we're going to discuss the quadrant angles. This is where the circle kind of comes in. I'll kind of introduce how circles and triangles relate nicely with each other. But let's say I pick a point anywhere on this particular circle. And I'm going to say that that's my point xy. And if we did what we did in the last example, and I were to draw a little right triangle, then you get a point on a circle, right? It still works perfectly fine. I have an xy and I could find an r. But notice at 0 degrees, I can't really do that, right? I just kind of get a line. At 90 degrees, I also can't do that. I also just get this line. At 180 degrees, I can't do that. You just get a line. And then at 270, you also just get this line. Same thing at 360, but that's the same as 0. All right? What you would do instead is you would just very simply use the x, y, and r definitions to find your r value, and then find your sine, cosine, tangent values. All right, so at 90 degrees, really any point on this positive side of the y-axis is going to work, but we stick with the easiest one at 0, 1. All right, that's also going to get us the ordered pairs of our unit circle, right? When we get to that lesson, this circle of radius 1 is where we get our values for the unit circle. All right, maybe you've heard of it before, but we'll get there eventually. But yeah, I'm just going to use x as 0 and y as 1. So I want to find x squared plus y squared equals r squared. And that's going to get us 0 squared plus 1 squared equals r squared. And then when you simplify, you get r equals 1, right? You guys can verify that, but it should be super easy. And so at 90 degrees, I can find these exact values, all right? So sine is going to be y over r, which is going to be 1 over 1, which is 1. Cosine is x over r, which is 0 over 1, so 0. And then tangent is y over x, which is 1 over 0, and anything over 0 is undefined. All right. Now I can do the same thing with cosecant, secant, and cotangent, right? Cosecant is r over y, which is 1 over 1, which is 1. Secant is, r over x, which is 1 over 0, which is also undefined. And then cotangent is going to be x over y, which is 0 over 1, which is 0. All right? So then we get those values at 90 degrees. We can do the exact same thing at 180 degrees, right? At 180 degrees, I have x is -1 and y is 0. I can do the same thing. I can do x squared plus y squared equals r squared to find an r value. And then you get -1 squared plus 0 squared equals r squared. And so I get 1 plus 0 equals r squared. And then again, r would equal 1. All right? So then for sine of 180, again, that's y over r, which is going to be 0 over 1, which is 0. Cosine of 180 is going to be -1 over 1, which is -1. Tangent of 180 is going to be y over x, which is 0 over -1, which is 0. All right? And the rest of these, you're just going to flip them, right? Cosecant is the flipped of sine. So this one's going to be 1 over 0, which is undefined. All right? Secant is going to be 1 over -1, which is still just -1. And then cotangent, I'm going to get -1 over 0, which is also undefined. All right? And then you can repeat this process for 270, 360, anything that lies on the x or y axis, you are able to find those values. All right. We kind of already discussed this a little bit. These are your reciprocal identities. It just says that sine, cosine, and tangent, if you were to flip them, you get cosecant, secant, and cotangent. All right, so we'll use this idea in the next page. So let's say I give you a secant value, like I do in number 3, and I ask you to find the cosine. Well, I already know that cosine and secant are reciprocals of each other, so then all I have to do to find cosine is flip it. It's going to be 3 over 5. And then it's simple as that. All right? Now, if I'm given cosecant, you can very easily find sine. All right? So I'm just going to flip what I have for cosecant, and I'm going to get -2 over square root of 6. And then I can square root of 6 on the top and the bottom to rationalize. And we get -2 square root of 6 over 6. And then 2 and 6 simplify to 1/3, so we end up with a final answer of -square root of 6 over 3. All right? So that one required a little bit more work, but the idea is still the same. You're just flipping the fraction to get your answer. All right? Similarly, if I gave you tangent, you could very easily find cotangent. All right? So these types of problems shouldn't be too hard. Now, in the next page and in the slide after, I'll show you how to find the values, or one way to find the values when it's not just a simple flip. All right, so there's a lot of information on this page. I'll go through it one by one. The solution intervals it's essentially just the range of these functions. All right, so you guys know this more familiarly as the range of these functions. So, for example, if you plug in a number into sine or cosine, you're always going to get numbers between -1 and 1. All right, and you can always test it in your calculator, right? If you want to double check, no matter what number you plug in, you're always going to get out of it just a decimal answer, right? So like a decimal that's between -1 and 1, right? Always. All right. Similarly, if secant and cosecant are reciprocals, then it's going to be the opposite. You're either going to get values that are less than -1 or greater than 1 in both directions, right? And then tangent and cotangent are all real numbers that you get out of it. The domain is not all real numbers for tangent and cotangent, but the range is, right? You get any number out of it. That's really just one way to maybe check your work. Like, let's say you're solving for, I don't know, let's say one of the problems is asking you to find sine, all right? And then let's say as your final answer, you get 5/4. Well, that doesn't really make sense because 5/4 isn't in our solution intervals. So I know that you probably made a mistake at some point. But that's just a way to check your work. That doesn't really come up so much right now. So let me just erase that. Again, doesn't really come up much right now. It will in the future. But for now, it's just a way to maybe check your work. What will show up are the Pythagorean and quotient identities. All right. So these Pythagorean identities, they're called a Pythagorean identity because you see in all of these squares, right? Your Pythagorean theorem that you guys are familiar with is a squared plus b squared equals c squared. So it's essentially just the same idea, just using trig functions in it. You are given these on tests and quizzes, so just always have it on deck, right? Always have maybe a little screenshot when you're doing your homework and stuff. Same thing with the quotient identities. This one I'll actually show you why it is the way it is, right? So sine, you guys know that that's y/r. Cosine, you guys know that that's x/r. When you divide, you keep change flip, right? y/r times r/x. R's cancel and you get y/x, which you guys already know is tangent. And you can do the exact same thing to verify cotangent, right? Cotangent would be cosine over sine. Let's actually put these into practice, right? So probably doesn't make too much sense just hearing about it, but in practice, you'll see where it comes from. Okay. These problems say to use the Pythagorean identities to find the following information. So number 5, I want to find sine and cosine, and I'm given a tangent value. All right, so the first thing you want to do is check your Pythagorean identities to see if anything has a tangent in it, right? And we do have one, right? It's 1 plus tangent squared equals secant squared, all right? Now, what I would do with this information is I'm going to plug in 4/3, and I'm going to get 1 plus 4/3 squared equals secant squared theta, right? And so I'm just going to solve this for secant, right? So 4/3 squared is going to be 16/9. And to turn 1 to have a denominator of 9, it would be 9/9. And this is going to get us then 25/9, which is secant squared theta, all right? And then I'm going to square root both sides, and then we're going to get secant squared theta, or not squared, sorry, secant of theta is plus minus 5/3, all right? It's actually not going to be plus minus, it's going to be one or the other, right? Now, how do we determine that? Well, I'll explain that briefly now, right? So in the corner, this isn't part of our actual problem, but I'm just going to explain something real quick, all right? We're given that our angle is in the third quadrant, all right? Let's just draw what that means, right? In the first quadrant, we have that x and y are both positive. In the second quadrant, I have that x is negative and y is positive. In the third quadrant, I have that both x and y are negative. And then in the fourth quadrant, I have that x is positive, y is negative. Well, think about the first quadrant, right? Both positive. Every single trig function that we use is going to be positive then in the first quadrant, right? It's going to use x and y some way, shape, or form. So I'm going to say all of our functions are positive in the first quadrant. Now in the second quadrant, x is negative, but y is positive, right? Think about the functions that use the variable y, right? And it's sine and tangent, right? So I know sine is y over r, and tangent is y over x, but x is negative, right? So really the only thing that would be positive in the second quadrant is sine, all right? Similarly, if you look at the third quadrant, right, x and y are both negative. So that means if I just have an x and I just have a y, then those functions are going to be negative, but whatever has the x and the y is going to be positive, right? Because negative over negative is positive. And that's going to be tangent, right? Tangent is going to be positive because it's y over x, right? And negative over negative is positive, all right? Same thing in the fourth quadrant. If you look at what's positive and negative, x is positive, y is negative. That means anything that has a y and an r, or an x and a y together is going to be negative, and anything that just has the x and the r is going to be positive. And that's going to be cosine, right? So in all of these, it's going to be these functions plus their reciprocals. So cosecant is also positive, cotangent is also positive, and secant is also positive, all right? So I just outlined what is positive and where, right? So all the functions are positive in the first quadrant. Sine is the only one that's positive in the second. Tangent's the only one that's positive in the third, and cosine's the only one that's positive in the fourth. All right? One way that I like to remember it, and one common way, is all students take calculus. All right? All students take calculus, so all are positive in the first quadrant. Students, sine, and its reciprocal are positive in the second. Take, right, so tangent and its reciprocal are positive in the third. Calculus, cosine, and its reciprocal are positive in the fourth, all right? So if I have that theta is in the third quadrant, we're looking in this region right here, all right? So that would mean tangent and cotangent are the only ones that are positive. Secant is not listed there, right? So it's not going to be plus minus. This one's actually just going to be negative 5/3, right? So I have secant is negative 5/3. That doesn't really help us because we're looking for sine and cosine. But I know based on one of our reciprocal identities that secant and cosine go together. So I know that cosine has to be negative 3/5, all right? And that answers that part of the problem. To find sine now, we can use another Pythagorean identity that relates sine and cosine. All right, so I know that cosine squared theta plus sine squared theta equals 1. So then what we're going to have is negative 3/5 squared plus sine squared theta equals 1. And so this is going to get us 9/25 plus sine squared theta equals 1. And I'm going to subtract 9/25 on both sides. And then the 1 I'm going to turn into 25/25. And then 25 minus 9 is 16. So I get sine squared theta is 16/25. And then I can square root both sides. And then I get sine is plus minus 4/5, right? And then again, think about theta in the third quadrant, right? If it's in the third quadrant, then tangent and cotangent are the only ones that are positive. Sine is not one of them, so I'm going to go ahead and erase that plus minus, and it's just going to be minus 4/5. All right? And so that's how we would solve a problem like this using the Pythagorean identities. All right? A little bit of a complicated example. Let's try the same thing with the next one. All right, this one's a little bit more straightforward, right? I have cosecant and cotangent we already have a trig function that relates cotangent and cosecant. So I'm going to use it, right? It's 1 plus cotangent squared theta equals cosecant squared theta, all right? So then I'm going to plug in negative a half in for cotangent, so it's going to be 1 plus negative a half squared equals cosecant squared theta. And so I get 1 plus 1/4, which I can change to 4/4. And so that's 5/4 is cosecant squared theta. Square root both sides, and then this is going to get us cosecant of theta is plus minus square root of 5/2. All right, and again in quadrant 4, well, if you think about all students take calculus, right, in quadrant 4, it's just cosine and its reciprocal secants that are positive. Cosecant is not one of them, so I'm going to erase, and it's just going to be negative 5, or square root of 5/2. All right, so it's a little bit of a more straightforward example, but that's how you would use the Pythagorean identities to find a trig function. All right, last few examples should be pretty straightforward. All right, so again, you can think of this one a couple different ways, right? I'm going to draw it. It's similar to one of the first few examples that we did. Negative 4, 0 is right there. You could draw it and notice that it's at 180 degrees. And then if you know the functions at 180 degrees, then you can immediately fill this in. Let's just say you didn't recognize that. You would use x, y, and r to figure these out, right? I know x is negative 4, y is 0, and then we can do x squared plus y squared equals r squared. So negative 4 squared plus 0 squared equals r squared. We get 16 is r squared, and then we get r is 4. All right, so then we already have that x equals negative 4, y equals 0, and r equals 4, and so you can just use x, y, and r to figure this out. All right, sine is y over r, so 0/4, which is 0, which means cosecant is going to be the reciprocal. So 4/0, which is undefined. All right, now let's do cosine. All right, cosine I know is x over r, so negative 4/4, which is negative 1. And that would mean secant is going to be the reciprocal, so 4/-4, which is also negative 1. All right, now we do tangent. It's y over x, right? So 0/-4, which is 0. And then when you do cotangent, you're just going to flip it, so negative 4/0, which is undefined again. All right, so something like that shouldn't be too bad, right? If you sketch it out, or if you understand the x, y, and r, shouldn't be too bad. You just get different values than we did in the first few problems. All right, now this page looks kind of crazy. It looks harder than it is. All right, you just need to recognize what angles you see here, right? I see a bunch of 180s, and I also see a bunch of 360s. All right, so let's draw these and figure out exactly what values they are. All right, secant of 180, right? I know 180 is over here, so I'm just going to pick a point that's pretty easy to use, right? Negative 1, 0 is 180 degrees. So I know that this has to be x, that has to be y, and then I know that r has to be 1, right? You can do x squared plus y squared equals r squared to figure it out, but we've already done this before, right? So I know that r has to be 1. And I know that secant has to be, it goes with cosine, so I know it has to be r over x, right? And r is 1, x is negative 1. That would make secant 1/-1, which is just negative 1. So then I get 3 times negative 1 minus 5 times tangent of 360. Well, 360 goes all the way around. So I'm going to use the point 1, 0 just to represent it, right? You could use any point. You could use 2, 0, a half, 0, but the easiest one is 1. And then we have an x and a y, and I know that tangent is y over x, right? So that is y over x, so 0/1, so 0. So then I get 3 times negative 1 times negative, or minus 5 times 0. So then we get negative 3 minus 0, which is negative 3. And so that one simplifies like that. All right, I can do the exact same thing with the next one. Tangent of 360 we just said is 0, plus 4 times sine of 180. Well, sine I know is y over r, and so this has to be 0 over 1, which is 0. So 4 times 0, and then plus 2 times cosine squared of 180. I know cosine has to be negative 1 over 1, and when I square it, I get negative 1 squared, which is 1. So I get 2 times 1. Simplifying this expression is just going to get you 2. All right? But that's it for this set of notes. Shouldn't be too bad if you practice and recognize how to do each problem, right? So I know part of it's new, but a lot of it does get repetitive and redundant, so adequate practice should be more than enough for this particular lesson.